Okay, so all right, so we're done with the first 3 chapters of the book already. It's so weird. Feels like we just got here. So on to derivatives. Now I will say that it seems like about time that we finally got around to doing our first little bit of calculus. Right? We've done 3 whole chapters in the book and hardly any calculus at all. Technically, I would point out I think limits count as calculus. Right? Okay. But certainly no derivatives yet, and that seems weird. So here we go. Now I'm going to start with a reminder about single variable derivatives. I think there's a lot of value in revisiting former topics on which you're going to generalize before you go on to the generalization itself. And keep in mind, I mean, the point is when you do a generalization, right, or an extension, whatever you want to call it, the idea is that you want to take certain features of the old version of the idea that you're going to retain. Certain fundamental, traits that define, what does it mean to be a derivative in this case, right? And of course, there's certain things that you're not going to retain because if you don't change anything, then you don't get a new idea, right? So I want to underscore exactly what I think it is that is fundamentally fundamental to the word derivative, not just peculiar to single variable derivatives, but fundamentally about a derivative, and then we're going to try to figure out how to apply those ideas in the multivariable context. So here we go. Y'all remember this formula for linear approximations of a single variable function, right? Hope everybody remembers that. And an easy twist on that is this formula, right? That how much the function changes, namely the difference between these two values, right? Delta f is approximated by, that formula right there, namely the derivative df dx times delta x. So now it might not get written this way in Calc 1 classes necessarily. Maybe they do, whatever. But I want to write it this way here to emphasize that what this derivative is doing here is this derivative is a relationship between what I like to call an input change and an output change. Right? So we've got this function, we've got input values, we've got output values. If you change the input by a little bit, you would expect that you would also change the output by a little bit also. And the relationship between the input change and the output change is the derivative. Of course, this is just an approximation, right? But nevertheless, that the expected, the best estimate relationship is the derivative. Now, here's another fact about single variable derivatives that I hope you will remember, and this is the chain rule. Now, again, it might have, you might be more familiar in seeing this with different variables, dz dx equals dz dy times dy dx, whatever. It's the same idea, just, different variables. And what I'm trying to represent here is suppose that, again, you have f as a function of x, and what we have here is a relationship between the velocity of the input. Like if here's your x-axis, here's your f-axis. If x is changing at a certain speed, so x changing at a certain speed, we would represent by dx dt. Then the output values of this function, f, will be changing at a certain speed, which we represent by df dt. And the relationship between those velocities is the derivative again. So notice that the derivative is playing an analogous role in both of these are different content. They're different sort of interpretation, different applications of the derivative, but in both of these cases, notice that the derivative is relating some sort of a change in the input values. Here it's a discrete change, here it's a rate of change. So some sort of input change is being related to the analogous output change by multiplication by the derivative. Okay. Oh, sorry, buddy. Didn't mean to smack you there. Okay. So this is one of the big takeaways I want to take for single variable derivatives, and that is that we're relating input changes to output changes. Okay, you make a noise there, don't you? Input changes to output changes, and in particular, the derivative is what you multiply by the one to get the other. Okay. And let me say that then a little bit differently. The derivative is kind of what you do to the input changes to get the output changes. Now, do in this sense is multiply, right? But just broadening, let's make a little bit less specific. Is it critical that it is a multiplication? If we're going to generalize to some other context, does it have to be a multiplication in order to be a relationship between input changes and output changes? And I'm just going to, let's broaden our minds a little bit. No, it doesn't really have to be a multiplication. He is going to get so tied up in knots under that. Oh well, so be it. All right. Okay, so in general, I want you to walk away from this first section of chapter 4 with the idea that the way you want to think about derivatives. And again, this is not the main way you think about derivatives in a Calc 1 class. The main way you think about derivatives in a Calc 1 class is slope of a tangent line. That plays a role. It's nice, I guess, but it's really not the most important way to think about derivatives. So I want y'all to sort of try to do what you can to change your point of view on single variable derivatives to derivatives are relationships between input changes and output changes. Okay. All right. So now we can draw a picture of these kinds of things. Now notice I'm drawing a graph here. Right? Here we have this graph where y is a function of x. I've given quite a bit of discussion to how arbitrary and really kind of peculiar that is. So anyway, I'm going to put this on the graph context here just for familiarity's sake. But anyway, that being said, here is a change in x. Here is a change in f. And the derivative is what you would multiply by this to approximate that. From a velocity standpoint, let's suppose that this point has as its image that point. Then if that input point were to just get up and start moving with some velocity, then the output would correspondingly start moving unavoidably with some velocity, and the derivative is the relationship between those velocities. Okay. All right. Okay. Is he making himself a bother, or is he okay? He's okay? Okay. All right. Okay, there's some examples here. I'm going to let y'all read these examples. It's just single variable calculus, right? No big deal. But do read through these just to make sure that you're familiar and that you remember all this kind of stuff. I know it was a while ago. What I have here, lastly, though, is just a reminder of the pictures that we just looked at. These are really morally the same pictures. This picture is just a rehash of this picture. Here, I drew it on a graph where we could see the curve representing the function. But notice, importantly, we have an x-axis on which there is a representation of a change in x. There is a y-axis on which there is a representation of the change in y. Here you go. Same thing, right? So here is a change in x represented by a vector on the x-axis, and a change in y represented by a vector on the y-axis. So you don't really need the graph in order to be able to make this interpretation of input changes and output changes. Okay. All right. Okay. So that was just a little bit of context. Now we're going to try to build up ideas of multivariable derivatives. By the way, here's one sort of I don't know how to say this, disappointment or difference in the multivariable context, but there's not going to be just a single notion of derivative in this multivariable discussion that we're going to have. There's actually a bunch of different kinds of derivatives, and they kind of build, the way I'm going to present them here, we're going to build upon, one upon the other until we build up to the really most fundamentally natural one ultimately. So it's going to take several steps. So we're going to start off, a little bit at a time. And my goal today is to cover 3 different sections. I'm hoping that we, is it 4? My goal is to finish 4.4 today. Right? So we're going to talk about several different kinds of derivatives. in today's lecture. So we're going to start with derivatives of parametric curves, and I'm going to start with derivatives of parametric curves because it's arguably kind of the easiest one. In fact, it's pretty straightforward. So here's the idea. There's a parametric curve. Remember, a parametric curve is a curve that is parametrized. So our curve is the image of the function. So another reminder, we're not talking about graphs here. When we draw a picture of a parametric curve, that is not the graph of this function. It's the image of the function. Totally different thing. Okay. All right. Yeah. So here's the definition I'm going to make of the derivative. Right there. And you might notice that looks kind of familiar. Doesn't that look just like the definition of a single variable derivative? At which point you might raise your eyebrow and say, hey, wait a minute. Last time we just gave some discussion about how you really can't do this, that this crashes and burns in the multivariable setting. Y'all remember that? We were dividing by a vector, for crying out loud. You can't divide by a vector. That doesn't make any sense at all. It's nonsense. So why can I do it here? And the reason why is I'm not dividing by a vector. I'm dividing by a scalar. H is a scalar. Why is H a scalar? H is a scalar because H needs to be just like T. T is a scalar. Why is T a scalar? Well, because I'm looking at a function of a single input variable. Right? The denominator is a scalar because the input is a scalar because the domain is R1. So the definition I've written down here critically relies on this being a curve, a parametric curve, so that the input is R1, the domain that is R1, so that the inputs are scalars, so I'm dividing by scalars. Is everybody on board? All right, so this is a limited, very limited application. Nevertheless, there's a lot of parametric curves out there, and this is, like I said, a good place to start. So this is our definition. Why are we using this formula? Mostly because it's familiar. We had a lot of success with this formula previously, so how about we give it a try and see if anything kind of cool happens. Remember, whenever you make a definition, you have to worry about, is this natural in any way, or is this just a bunch of formulas on the page? Is this arbitrary, or does this connect to natural things? So what we want to try to figure out now is this in any way geometrically or physically natural? All right. First, a little bit of algebra. I'm going to show you how to compute derivatives of parametric curves. There's a bit of a calculation here, but ultimately all these steps are familiar. So there's our definition. Notice, first thing we need to do is we need to take this numerator. It consists of a difference of two vectors. I need to subtract those two vectors, and I remind you that the way we subtract two vectors is one component at a time. Right? You want to subtract this vector minus that vector? Well, first subtract the first components, then subtract the second components. Ancient history, old news, chapter 1, right? That's how vector addition and vector subtraction, component-wise, we call it. Because it's one component at a time, each component individually. Okay. Cool. So that gets us to here. Now, next thing we need to do, we need to divide a vector, you see there, by a scalar. How do you divide a vector by a scalar? Well, again, a chapter 1 reference, component-wise. We wrote down a reasonable motivation for what it should mean to multiply a vector times a scalar, and it ended up being very natural to do it one component at a time. Okay, so that leaves us then with a limit of a vector expression, and you may recall the very last thing we said about limits was that limits of vector-valued expressions are computed component-wise, one component at a time. So the limit of this vector is the vector of individual limits. And hey, good news. Well, we now recognize a bunch of these expressions, like this expression right here. That expression R1 of t plus h minus R1 of t all over h. Take a limit as h approaches 0. That's exactly, not reminiscent of, not approximately. This is exactly the definition of the single variable derivative of that first component function R1. So it's just literally the derivative. Yeah. Okay. Yeah. Okay. So good news. Because the entire process here of computing derivatives of parametric curve, every step in that process is component-wise. The resulting formula is that derivatives of parametric curves are computed component-wise. It's great news. You couldn't ask for a more sort of like expected answer. In fact, without even doing this calculation, I would be willing to bet that if I had asked y'all, if I'd taken a poll, hey, here's a vector valued function, take the derivative of it for me, not knowing what that meant or having any previous knowledge of how to do that, I'll bet this is what you would have done. That seems just extremely natural. Okay, so it's algebraically natural. Is that persuasive? Yeah. Having nice algebraic properties is cool, but it's not. I'm not gonna hang my hat on something because it's algebraically convenient. So let's look at the expression again. Here's our formula for derivative, and let's try to look at it geometrically. What does this look like? Well, notice I'm looking at a point on the parametric curve. I'm then looking at another point on the parametric curve that comes from going h units of time later. So there's 2 points on the parametric curve. I'm then going to take the difference between those 2 points. That's going to be a vector from green to blue. And then that gets divided by h, and we take a limit, etc. Okay, so let's not get ahead of ourselves. There's a point on the parametric curve. Here's that nearby point, h units of time later. The numerator is the difference. Right? That's that numerator there, the difference between those 2 points. And let's think about what happens now as h gets small. Eventually we're going to take a limit as h approaches 0. As h gets small, these 2 points get closer and closer and closer to each other. The numerator becomes this increasingly small vector, which is a familiar construction, right? That's the problem that was happening when we were looking at derivatives in a single variable context. So in order to keep things from just disappearing, we divide by h, right? That same h that we have there, divide by h. Now altogether then, this expression if you take an increasingly small difference vector and then divide by the correspondingly increasingly small elapsed time, h, small divided by small, gives you something that you could reasonably expect would not vanish. Right. This is all really familiar from Calc 1. Right? This is a lot of the same ideas, just sort of a different sort of picture. Okay. All right. So that's what we're looking at. Now let's think more specifically. Notice that this difference vector from there to there is not tangent to the curve, but as h gets smaller, the amount of the sort of the curve that it kind of chops off, if you will, between these 2 points, as h gets smaller, that amount gets smaller and smaller. And so I am going to appeal to your geometric intuition that most of the time, generically, for nice parametric curves, what you would sort of expect is that in the limit you would get a tangent vector that's just tangent to the curve, going the same direction that the curve is at that point. Yeah? Everybody good? So it looks like he's found a spot over there to settle down. All right, good. Okay. Okay, so that's the first thing that we're going to notice about this this derivative. That's already geometrically natural. The derivative vector is a tangent vector to the parametric curve. That's undeniably geometrically natural. Okay. So we're already a little bit persuaded that this is a natural thing to write down. Okay, moving along. Now, what else can I say about it? We've talked about the direction that this new derivative that we've defined points. What can we say about the magnitude? How big is this thing? Right? This is a vector. We understand the direction that it's pointing. We need to understand magnitude to understand the rest of the vector. And so I'm just going to take magnitude of both sides, and I'm going to not worry about the fact that the magnitude of a limit, the limit of a magnitude, are those the same? Let's not worry about that. It's not our problem in this course. And just taking magnitude inside of the limit, notice the magnitude of that difference vector is just a distance. The magnitude of the elapsed time is a time. What we have here is distance divided by time. We're taking a limit as h approaches 0 of distance divided by time. That is the exact definition of instantaneous speed. Right? So, okay, great. So what we have then is this derivative vector is natural both in its magnitude and its direction. It's a tangent vector whose magnitude is the speed of the parameterization at that point. It's all totally physically natural, geometrically natural, depending on how you want to look at it. In fact, here's how natural this is. This was one of the very first examples that we ever gave of a vector. Think back to the first day of class. We talked about, what's a vector, and the very first one was we talked about a displacement, right? A direction combined with a magnitude representing how far you go in that direction. But our second example was velocity. Suppose you are moving in a certain direction and that you have a certain speed. Let the magnitude be that speed. That corresponding vector we call the velocity vector. So that's what the derivative is here. And that is very fundamentally physically natural. Okay, how are we doing? Everybody on board? Okay, is he getting himself tangled up? Not really? Okay, all right. Sorry? Smart dog. Okay, yeah, he knows his topology. Okay. Okay. Right, so let's see an example here. Suppose we have a bird that is flying along with position as a function of time given like this. Now, by the way, this is a familiar parametric curve. Y'all may recall we studied this parametric curve. This is the one it does like this. It's a helix that's spiraling up, right? So birds do this sometimes. They catch an updraft, right? And they just they spread the wings and they just and then maybe they kind of circle around as they go up. Okay? So I claim this is plausible. So let's ask then, what is the bird's velocity as a function of time? We know position is a function of time. What's the velocity as a function of time? Well, the derivative is the velocity. So all I have to do is take the derivative of my given position function here. And great. So the derivative of that parametric curve. How do you take the derivative of a parametric curve? One component at a time. Right? Just like you would hope. Once you're taking the derivatives one component at a time, notice individually these are easy and extremely familiar calculations, right? The derivative of that first component, cosine t. Well, hey, cosine t is a scalar valued function. This is a Calc 1 derivative question. So derivative of cosine minus sine. Just like it always was. So, one step at a time, this is a very straightforward calculation. Everybody on board? Okay. All right. Okay, yeah. Mm-hmm.
Can we always just use basic derivative rules, or do you ever want us to use the actual derivative?
Oh, unless the problem specifically tells you or in some way strongly implies that you should like work out derivatives directly from the definition, yeah, you're very welcome to just use all your old friends, your derivative rules from Calc 1. Totally fine. Chain rule. By the way, make sure you know all those. Just as, reminder. Chain rule, product rule, quotient rule. Here's one a lot of students are shaky on. Logarithmic differentiation. Now, not everyone has seen logarithmic differentiation. If you haven't seen logarithmic differentiation, I'm pretty sure I put a homework question on one of these first few sections here. I don't remember which one, that involves logarithmic differentiation, because it's a neat trick. It's not that hard, and I feel all Calc 1 classes should cover it. Whether they do or not, it's a separate question. But anyway, if you have not seen logarithmic differentiation before, come to office hours. Let's talk about it. It's not that big a deal, but it's a neat trick. Okay, great. So yeah, good. Okay. All right. Now, by the way, y'all may recall this idea here. Here we go. That a derivative is a velocity. That connection might look somewhat familiar. So here's how that's familiar. I just want to kind of connect the dots. Back in Calc 1, y'all worked a certain number of examples where the deal was that, so you got a car driving along a road that was a perfectly straight road known as the x-axis, right? And car is driving along the road where the car's position as a function of time is given by some formula, and they want you to compute how fast the car is going or something like that, right? And they, make the observation that, well, when position gives you, is given by a function, then the derivative is the velocity. And it's one of the applications of the derivative. Well, they didn't say it at the time, but now that we have a context, let me point out that if they were saying that that the car was driving along the x-axis where position gives you the value of the function, they were parametrizing the x-axis. That was a one-dimensional parametric curve. That was a parametric curve in R1. It was a really boring place to do a parametric curve, right? Nevertheless, that's what it was. You've actually seen, in other words, derivatives of parametric curves previously. It was just one-dimensional parametric curves. And so the idea that, here for 2, 3, or higher dimensional parametric curves, the idea that the derivative is the velocity is actually a callback to these old examples that y'all saw in Calc 1. Okay. All right. Here is another kind of question that you saw back in Calc 1, and that is, suppose velocity is a function of time. How do you find position? And you're given an initial value, an initial position. How do you recover that position as a function of time? So I hope y'all remember questions that were kind of like this, a one-dimensional version of this. So same deal. If velocity is the derivative of position, then position is the antiderivative or an antiderivative of velocity. And it's going to be more structurally the same kind of calculation. So I'm going to go through it quickly. So position is an antiderivative of velocity. Velocity is given by a vector. Antiderivatives are computed component-wise because derivatives were computed component-wise. That just stands to reason. So what you've got here is, this is a multivariable calculus question. This is a multivariable calculus question. This is 3 separate single variable calculus questions. So make sure you remember all your antiderivative rules, right? So integration by parts and substitutions and trig integrals and, there's a long list of various rules you have to know. And I'm sorry to report that the need for those does not go away as you get higher and higher in this branch of math anyway. So make sure you're good at all that stuff. It is assumed and it is going to show up on, obviously not this first midterm, but on the second midterm and the final, there will be There's going to be integrals. Okay, so 3 easy old integrals. Okay. Now, one word of warning I want to give, these constants right here, there is a temptation to be a little sloppy in evaluating those constants. A lot of students mistakenly believe, because of a very unfortunate coincidence that shows up in high school calc classes, that those constants are just the initial values. And the reason students believe this is because in a lot of high school calculus classes, they've worked a lot of these kinds of problems, and in every single one of the problems that they worked in their high school class, they ended up being the same numbers. Hard to deny the pattern, right? Well, let me show you why that pattern holds. The reason that pattern holds for the examples that you saw in high schools is because usually they would give velocities that are polynomials. Polynomials, when you take antiderivatives, give you stuff over here that's also all polynomials, but even more, polynomials with no constant terms, right? Any polynomial, when you take its antiderivative, all the terms are going to have at least one factor of t. And when you plug in t equals 0, all of these terms would just disappear in a puff of smoke, turn into nothing but zeros because there's a factor of t in every term. And if these were to just be 0 reliably every time, then yeah, what you'd end up with is that those numbers end up equaling these numbers. Right? Well, that's a peculiarity. The idea that all velocities must be polynomials, that's insane. That's not true at all. Right? So note what's going to happen here in this example. When we plug in our initial condition that, at time equals 0, plug in t equals 0, evaluate these functions, notice that not all of these antiderivative, other than the integration constants, not all of these terms ended up being 0. These happen to be zeros, right? And so those constants end up being those constants. But here, the antiderivative was cosine. Cosine of 0 is 1. So it is simply not going to happen, in this case, that C1 would be 3. In fact, as you see there, C1 is 4. So these constants, these integration constants, compared to these initial conditions, not the same. Okay, so 2 things to keep in mind on this. For one thing, don't make the mistaken belief that these numbers will always be those numbers and, try to save yourself the trouble. Because you get wrong answers sometimes. More to the point, more importantly, remember, this is a class that's not about answers. This is a class about ideas and communication of thoughts, right? And mathematically valid reasoning. Right? And even if it were to work out that by simply, asserting, these constants give you those constants, and even if you got lucky and you got it right, even if that happened to be true, the reasoning is not valid, and you would not get points for that. Right? So make sure that we're clear on that that point of view there. You get points on exams for reasoning that makes sense, not for answers that happen to be correct. And is there any question about this? Is everybody totally on board with the distinction? Okay, cool. Okay. All right. Okay. All righty, moving along. Okay, so I'm going to talk about a new kind of derivative now. It's called a directional derivative. It's a really important idea in multivariable derivatives. This is where we're going to go back to, in fact, let me flip back here real quick, all this business about single variable derivatives. Remember, in both of these cases, we found that the derivative was the relationship between input changes and output changes. right? And this is this big point of view I want to push about how to think about derivatives. Derivatives should be thought of as relationships between input changes and output changes. So what I want to do is now let's go back to our multivariable context here. Let's see, we're almost there. Here we go. No, that's not it. Here we go. Here I have a multivariable function. Very importantly, notice that my domain now is no longer just a single variable. Right? It's not R1. So this is not a parametric curve. We're done with parametric. We have a truly multivariable function here. We have multiple input variables. If I say change the input, your response has to be which way? I could, from this point in the domain, I could move this way, I could move that way, I could move this other way. You want to move? Okay, you got to have to be a little bit more specific. Which way do you want to move? So that said, this function, if you have an input point, A, that'll have some corresponding output value, f of A. If you were take off and start moving with some velocity in the domain. Now, this is just an appeal to your understanding of how functions work. But if you wiggle the input, if you start changing what you put into the function, then you are correspondingly going to get changes in what comes out of the function. Said differently, if your input point starts moving with a velocity, your output will start moving with some velocity. I don't know exactly what, but there will be a velocity there. So what I want to do, what I want to call a directional derivative, is this is the name that we give to this scenario. The directional derivative says we take as an assumption that we have some point in the domain, and we're then moving from that point with some velocity. And from that point with that velocity, the directional derivative is what is the velocity of the output. So that's the directional derivative, this thing in green here. Okay. And notice now, I just to call back again to section 4.1. The directional derivative is, as promised, a relationship. It's a connection of some sort between input velocity and output velocity. Input change, output change. Right? Now, what it isn't, it's not something that you multiply. Right? That didn't carry over, at least yet. By the way, give it time. We're going to make such a connection later. But as it stands, it's not a multiplication. Okay, so the big looming question we have then is how do you compute such a thing? And I'm going to compute it in what I feel is a very brute force kind of way. We're going to just directly compute. I'm going to start off by saying, well, look, if you're at this point and moving with this velocity, then you're moving along a parametric line. And I'm gonna write down that parametric line. Let's see here. Position on that parametric line is A plus TV. Right. Calling back to chapter 1. Does everybody remember parametric lines? By the way, notice having parameterized it like this, and of course there's lots of parameterizations. Notice that this point here, A itself, that's the point that you're at when t is equal to 0. So let me just document that for the record. This parametric line, as required, goes through A, has velocity v, but specifically we are at the point A and moving with velocity v when t is equal to 0. All right. Well, for each one of these input points, as you're moving along the line, each one of those is a point in the domain that you can stick into the function, and out then comes a point in the target. And this function f is, oh my gosh, who knows? It's some arbitrary function. I don't know. So even though we're moving in a straight line in the domain, the output is liable to be some curve of some sort. Who knows? You cannot assume that this f is, for example, a linear transformation. Not at all. So, to connect the dots a little bit too literally, as you're moving along this parametric curve in the domain, your output, your image, is then going to correspondingly be moving along a parametric curve in the target. And keep in mind, our goal was to find this velocity vector in the target. I now see that my movement in the target is, I have this green curve is position as a function of time there, and I just want to then take the velocity, the derivative then of this parametric curve. And it's easy to write down the details here. The parametric curve, wrong tool. The parametric curve is just f of the blue parametric curve. So it's f of a plus tv that's that green parametric curve right there. And the directional derivative I'm interested in is the time derivative then of that. So there you go. That's how you do it. It's, like I say, very brute force. We just parameterize and just keep track of everything that we're actually interested in this scenario and compute it up. So here's, I've just effectively reproduced this picture here. So here's our parametric curve in the domain. There's a parameterization of it. Right? Plug that into the function, and that gives you that parametric curve. We are interested in the velocity of that parametric curve. We take the derivative. Okay. So that's, you'll notice here then the definition that I give for a directional derivative. Here it is. It's exactly what we just wrote down here. There's our input parametric line that I plug into the function, thus giving me my output parametric curve. Take the derivative to recover the velocity of that output parametric curve, and that is the directional derivative. Okay. One detail. Don't forget. A little micro detail. I want to know this velocity of the output at this point. I want to know the velocity of the output when my output is at this point, namely when my input is at this point. I didn't parameterize this line because I want to know, what's the velocity over here, right, at some later value of t. The only reason I really parameterize this line is because I need to, at this point A, have some sense of motion. I need to be able to talk about velocity and what that means, right? So it is at this point A that I actually am interested in what's going on here. And at this point A, t is equal to 0. So going back down to the definition then, note this little detail. We take that derivative, and having taken that derivative, we then subsequently plug in t equals 0. Okay. Everybody, yeah.
Is the t in the parametric, like the parametric different? Like parameterizing the line for the velocity, is it different from the time itself?
There's only one t. So this t equals 0 that we plug in here to describe where we're interested in. Yeah, that is the same t that describes the parametric line in the first place, and it's the same t. This a plus tv is the parameterization of the line. Yeah, all of these t's are the same t. Yeah, totally. Yep. Okay. All right. Okay, notation. This is it's just notation, and by the way, not every book uses the same notation. I think this is pretty common, though. There's the notation. The idea is, we want to take a derivative of this function f. If you're going to take a derivative of f, you got to write down what f is. We're taking a derivative. Derivative says, we're gonna move in the domain and want to know what the output movement is of the target. And so capital D for derivative, no surprise there. But notice you have to have a subscript, because while in Calc 1, if you say change the input, yeah, cool. There's only one input, there's only one way to go, there's no ambiguity here. Here, remember, we have to specify, you're going to start moving in the domain? How so? A lot of options. You've got to tell me what that velocity vector. So there's not just a single kind of directional derivative of f. It wouldn't make any sense for me to say, what is f prime? F prime would just mean, hey, change the input. Right? A little short on details. How are you changing the input? So you've got to indicate with a subscript here, what is that velocity vector in the domain? And of course, then, just like any sort of derivative, you've also got to indicate what is this base point that you're at. So where is it? Where is this point A from which you would like to know what happens if you move the velocity vector? Okay, so that's the notation. It's how it's all sort of assembled, and you pronounce this the directional derivative of f at the point A with velocity v. Yeah. Okay. Alrighty. So now before I go on, this is I wish this weren't true, but there is an inconsistency in how this term directional derivative is used. I'm defining directional derivative here the way I think most mathematicians use it. But there is a different use of the word that is used in some textbooks, including the textbook that Math 212 uses during semesters. So this is very weird. So the term directional derivative in these other textbooks, some of the reasoning goes, the base of the word directional is direction. Directions are independent of magnitudes. So directional perhaps should mean that we want a vector that sort of factors out any magnitudes. We don't want to think about the magnitude. We don't want to think about the speed here. So to factor out that magnitude, the result is a unit vector. So in a lot of books, this term directional derivative and all the formulas that I just wrote down are applied only to unit vectors v. And semantically, I get where they're coming from, right? But the world is full of scenarios where you're moving with a velocity that is not a unit vector velocity. And I think that to constrain oneself for semantical reasons is really, I don't know. I just think that's a weird choice. Like I say, my understanding is that most mathematicians think of directional derivatives the way I'm describing here, and I will define in the next section a related idea called I'm going to call unit directional derivatives. And unit directional derivatives that I'm going to talk about later are what other books are talking about in those cases. Okay. And there are some cool things about unit directional derivatives. Absolutely. And we'll talk about all that stuff later. I feel that the term directional derivative should be broad. Like that. Okay, so anyway, that's unfortunate, but it is the way it is. Okay, so reminder, what directional derivatives are. Directional derivatives are a connection between input changes and output changes. Right? Again, it's not something you multiply. It didn't work out that way. But it is if you give me an input velocity, the directional derivative is the output velocity. If you give me an input change, some displacement, then the directional derivative is the output change. An approximation, that is, of the output change or the output displacement. So just like we had intended, just like we were sort of planning. Now, just a couple of contexts that you can make sense out of this. Here's one. Let's suppose, notice the pictures that we've drawn are multivariable domain, multivariable target. Let's think through, what these might look like in different contexts. So here, notice I have a scalar valued output. And so, what would this look like? And here's, I think, a nice way to think about this. So suppose the domain here is, some region of land, I don't know, map of the United States, whatever, some map of North Carolina, what have you. And, we've talked about several different real valued functions defined on these spaces. So, for example, we've talked about temperature as a function of position. Right? We've also talked about humidity as a function of position, altitude as a function of position. So what does the directional derivative mean here? Directional derivative would just say, well, hey, suppose I'm in my car and I'm at this location and I'm driving with a certain velocity. I'm going in the direction the road is going, and moving with a certain speed. Thus, I have a velocity. Then I could reasonably ask, how fast is the altitude changing? Right, and that's a reasonable question. If you're, that doesn't happen a lot around here, super flat, right? But if you're in Colorado or something and you're driving along I-70 and you notice you're going uphill, you might be thinking, I'm gaining altitude pretty fast here. A very reasonable thing to want to know is, how many feet of altitude per second is my altitude increase? What is the rate of change of my altitude as I drive, at this point on I-70, moving in that direction with that speed? Okay. So that's what a directional derivative would tell you. That's the interpretation in that context. That make sense to everybody? Why don't you come sit down? Okay. Come on. Okay, there you go. There you go. Good night. All right, we'll see if that takes. So here's another context. What if you have a single variable input? What does a directional derivative mean here? Well, again, input velocity, output velocity. You notice that the picture we have here is suggestive of something familiar. We've talked about parametric curves. Doesn't this look like a parametric curve? We have one input parameter, and we have an output curve in this target space. So this is a lot like a parametric curve, and the directional derivative is very closely related to the derivative of a parametric curve. The only difference is that here, in this case, we allow for different possible input velocities. And notice that when we were talking about derivative of parametric curve, that wasn't really a thing. We just, you give me a parametric curve, we talk about the derivative. The input changes, period. I want to know how fast do the outputs change as you change this variable. And that didn't leave open the possibility that we might have faster velocities in the input, slower velocities in the input. Right? So in order to make these ideas connect, if the input velocity is 1, if this input velocity is 1, then the directional derivative is the velocity of that parametric curve. Okay. All right. Okay, let's get our hands dirty. Let's do one. Here is now we're going to start off with real valued, single output value. That's computer directional derivative. So, function of three variables, and inside of our three-dimensional domain, let's suppose that we are at this point, 1, 2, 0, and that we are moving with velocity 2, 1, 3. All right, so we have an input point and an input velocity. Very reasonably, I could ask, what is the output velocity? What's the rate of change of these output values? And this is a straight up plug and chug. So here we go. We parameterize our parametric curve. So there's your parametric curve. A plus TV is a parametric curve. Now that's just a matter of plugging in, A plus TV. We know A, we know V. There it is. Okay, so there's our parametric curve. We're going to take our parametric curve and plug it into the function. Now, careful. What was our function? Our function was x squared plus yz. So first variable squared plus second variable times third variable. Okay, let's do that down here. So x squared plus yz. So all I did in that step is I just directly plug in to the given function. Now I've got a little bit of algebra to do. That's just algebra. Multiply stuff out, collect terms. Y'all can do that. Okay, so this is telling you then, as I move along that parametric curve, this is giving the output value as a function of time. I want to know the output velocity, so I've got to take the derivative. That derivative Calc 1 problem is that. After having taken the derivative, I then need to plug in t equals 0. And you see we plug in t equals 0, we get our final answer, which is 10. Yeah. Okay. Everybody good? Any questions? Yeah, okay. Classic mistake students make a lot is decide to go ahead and get this, let's plug in t equals 0, let's get that done, let's get that out of the way as soon as possible, right? And notice, you can't do that. You can't plug in a constant value of t before you take the derivative. That doesn't make any sense at all. So don't step on that landmine. Make sure to, only after you've taken the derivative can you actually plug in for the given value of t. Okay. All right, here's another one. Vector valued example this time. So, here's a really multivariable function. It's got 3 input variables, 2 output variables. And let's compute again, inside of the domain. This input point starts there and moves with that velocity. I'm setting it up with the same starting point, same movement velocity, because, whatever. Okay, quit. You're making a bumping noise with your tail, buddy. Okay. What's the velocity of the output? Well, keep in mind here, the velocity of the output, that's going to be a vector velocity. The outputs are locations. They are vectors, right? So the derivative of those outputs is going to give me an actual velocity vector, not just a speed this time. Okay. So here we go again. Now we've already parameterized the input line, this parametric line in the domain here. This is just my way of quantifying what it means to be at 1, 2, 0, moving with velocity 2, 1, 3. There. So there's my my input parametric line. Plug into the function. Now again, let's remind ourselves, what is the function? xy times yz, xy comma yz. So x, y, and then y, z. That's just plugging in. Right? And then, yeah, you got to multiply stuff out. A little bit of algebra. Take the derivative. Now, this derivative here, this is the derivative of a parametric curve. Don't forget, we have a new notion of how to take derivatives of parametric curves. It's done component-wise. So, take the derivative of the first component. And then take the derivative of the second component, right? It's exactly as you would hope. And as usual, having taken that derivative, plug in t equals 0, and there's your output velocity. And notice it's a vector, and as well it should be, right? This should be a vector. Our function is, let's see here, our function was from R3 to R2. If I were at some point here moving with some velocity in the domain, my output would be at some point moving with some velocity. It better be a vector. Yeah? Anybody on board? Okay. Okay. All right, there's another couple of examples I'm going to let you all read on your own. The last observation I want to make before we take a break is that just like parametric curves, just like limits, just like a lot of things we've seen here recently, directional derivatives are computed component-wise. And why this is true is actually a pretty straightforward observation. Now, it's a big construction, this derivative, this directional derivatives, this big construction formula. But ultimately, don't forget, a directional derivative, it's the derivative of a specially constructed parametric curve. And we already know that derivatives of parametric curves are computed component-wise. So this being just a special example of a derivative of a parametric curve, it too computed component-wise. Last quick observation, this being computed component-wise, a nice exercise for you to do on your own, I think. We go back to this example, right? And we just computed the directional derivative of this vector-valued function. Do this. Take just this out, this first component, right? Throw away the second component. Look at this as a function, a real valued function here. Just xy. Take its directional derivative at the point A, moving with velocity v. Go through that calculation, compute what that individual component directional derivative would be. And then likewise, having done that, do that one. Compute the directional derivative of just the second component individually. Same base point, same velocity. And what you will find is that when you do those calculations, not only will you get 5 for the first one and 6 for the second one, but you will find, and it's going to jump off the page pretty fast, that you'll notice that in fact the calculation, as you're getting this 5, you'll get that 5 because you were plugging in t equals 0 into there, which came from taking the derivative of that, which came from that multiplication. Right? In other words, the calculation itself is the exact same calculation that you just got through doing. Effectively doing them as a vector simply is doing two entirely parallel calculations that I suppose you can do individually if you'd like. Anyway, I think it's a good idea, a healthy exercise. Everyone should do that at least once. Yeah.
So this is from R3 to R2.
Yeah.
Still start with a parametric
So that's right. So this is R3, right? So inputs in this function are points in space, and independent of the dimension of where you're living, right? If you're at a certain point and moving with a certain velocity, the way that you kind of would get your hands on that is by it's always that's it's in this course. It's always going to be a line. Now, if we wanted to be really uptight, careful, rigorous mathematically about this, then we would have to show that no matter what curve you pick, be it a straight line or possibly a curve, as long as it's at that point moving at that velocity, that you would always get the same answer. And it's not technically obvious, but it's pretty believable. And for Math 212, yeah, we're just going to use straight lines. I'm just going to assert that for sufficiently nice functions, we're only going to deal with sufficiently nice functions. It doesn't matter. Always use a straight line. Doesn't make any difference. Yeah, great question. Yeah. Okay, this is a good stopping point. We're now done with directional derivatives. So we will pick up here with unit directional derivatives in, let's say, 10 minutes. So how about we'll say 11:20. See y'all at 11:20. Okay.